We are seeing, I think, just an enormous shift in artificial intelligence right now. For years, we've gotten used to AI systems being, well, being passive tools. You gave them an input, they give you back an output, a document, an image, a calculation. They were great at structured tasks. But that whole era of passive AI it's ending fast. We're moving into a world where AI systems are becoming active. They're becoming autonomous decision-making entities, and they're operating in the real world.
That is the monumental change, and the research community has a name for it: Agent AI. We've just finished a deep dive into the sources that detail this exact transition, really exploring how the incredible capabilities of these foundational models, specifically large language models, LLMs, and visual language models, VLMs, are being integrated to build these really sophisticated multimodal agents, agents that can actually interact.
So our mission today is a true deep dive. We need to unpack this new paradigm. I mean, what exactly elevates a powerful AI model to an actual agent? And we have to explore the pretty severe technical and societal challenges that come with integrating these powerful and, sometimes erratic systems. And then finally, we're going to look at three fascinating, really high-stakes domains where agents are already taking action: gaming, robotics, and, crucially, healthcare.
To understand why this feels like such a profound moment, we actually need to look back, way back to 1956, to the Dartmouth Conference, which was the very genesis of the AI field. The initial goal wasn't just, computing. It was creating artificial life forms that could collect information and interact meaningfully with their environment.
So this idea of autonomous agents, it's not new at all. It's the original mission statement.
Exactly. There was an early attempt, Minsky's copy demo robotic system in 1970, but the complexity of creating a holistic system with perception, memory, action, it was all just too much for the computing power they had back then. So the AI field, it just splintered. It broke into all these specialized subfields like vision or language, and we got really bogged down in the parts.
And lost sight of the whole.
Precisely. The current push for agent AI is a philosophical return to what's called Aristotelian holism. Aristotle believed the whole is greater than the sum of its parts, and central to this idea is understanding the final cause.
Okay, that sounds incredibly abstract for a piece of code. What does final cause actually mean for a modern AI agent?
It means moving beyond a system that just knows how to compute a response to one that understands why it exists and operates. For an agent, this means having long-term planning, persistence across multiple tasks, and the ability to autonomously handle unexpected changes, all while keeping its ultimate goal in mind. It's about coherence, not just capability.
Okay, so let's unpack this foundational shift. It's the sheer reasoning power of the LLMs and VLMs, their ability to handle complex reasoning, linguistic nuance. That's what makes the holistic agent suddenly possible, right? It shifts AI from being that passive tool for structured tasks to an active agentic role.
That's the catalyst. And if you look under the hood at the architecture of a truly integrated agent system, it's designed as this holistic closed loop. It combines 5 key submodules. It starts with the environment perception module, which takes in data, visual, language, sensor readings. Then you have a learning module. And the core brain function is the memory module. That's where you find knowledge, logic, reasoning, and inference.
So memory isn't just a database. It's the place where the agent is actually constructing its worldview and drawing conclusions.
That's right. And that reasoned worldview then feeds into the action module, what the agent does physically or digitally. And finally, the cognition module, which sort of oversees the whole loop. It covers thinking, sensing, and what the sources cautiously call empathy.
Wait, I have to pause on that. Empathy. That feels like a massive philosophical leap. Are we talking about AI experiencing emotion?
No, absolutely not. True human emotion.
Yeah.
But in the context of agent AI research, empathy refers to the system's ability to sense and interpret human intent and emotional state so it can adapt its actions. For, say, a therapeutic agent or a collaborator in a game, sensing frustration or confusion in a user is critical for effective interaction. It's a functional definition, not a philosophical one.
Right. Thank you for that clarification. That's crucial. Now, if we want these agents to be efficient, just relying on a massive frozen general-purpose LLM, it seems clunky. Our sources introduced a purpose-built alternative architecture, the agent transformer.
Yes. The agent transformer is all about efficiency and customization.
Yeah.
Traditional transformers take language tokens, and sometimes visual tokens, as input. The agent transformer adds a third, really crucial input type: agent tokens.
Agent tokens. Why do we need a dedicated space for those? Couldn't we just prompt the LLM in plain English, something like, robot move the gripping arm to 12 degrees?
You could, but it's often highly inefficient. and unreliable for precise real-world tasks. Agent tokens reserve a specific, specialized subspace for these agentic behaviors. Think about a robot arm needing to move to a precise angle, say 12.45 degrees. Trying to encode that precision reliably in natural language is really difficult and risks, token drift.
So the agent tokens represent the output actions or the tool calls directly.
Exactly. For a robotic agent, the tokens might represent precise controller inputs, joint angles. For a digital agent, maybe a specific API call to an external tool. And there are three key advantages to this. First, it's easy customization for specific tasks. Second, you get improved explainability. Developers can actually access the probability scores for those agent tokens to understand why the model chose that specific action.
And the third, which seems critical, involves cost and compliance.
Correct. Smaller specialized agent transformers can be way more auditable, easier to debug, and cheaper to deploy than constantly calling some huge proprietary general-purpose LLM. And that's essential for compliance in regulated sectors.
That provides a huge justification for why this architectural shift is happening. But speaking of massive foundation models, if we do use LLMs or VLMs as the brain, we immediately run into their biggest flaw: hallucinations.
Hallucinations are the existential threat to agent reliability. And the sources, they helpfully distinguish between two types. So imagine the agent is summarizing an article you gave it. An intrinsic hallucination is when the agent generates content that directly contradicts the source material. It says the author was Jones when the source clearly states the author was Smith.
Okay, so it's a direct contradiction. And the second type?
The extrinsic hallucination is when the agent generates information that is just totally ungrounded. It wasn't in the source material at all. It just invents a non-existent third author, Williams, in addition to Smith and Jones, just filling space.
And VLMs, the visual models, they also suffer from this when they're interpreting images.
Oh, they absolutely do. VLM hallucinations are often caused by the model's over-reliance on the statistical co-occurrence of objects in the training data. If it sees a train track, it might just invent a train, even if no train is visible, simply because those two things appear together so often in the data. The primary technical solution pathway to mitigate all these risks is retrieval augmented generation, or AIR.
Which means the agent is constantly checking its work against some external verified knowledge source.
Precisely. AIR grounds the agent's outputs. It uses these external knowledge retrieval mechanisms to check for contradictions before it generates a response. It basically forces the agent to verify its memories.
Okay, so IRGA handles technical truth, checking facts against sources. But what about the models learning human untruth, things like societal bias and lack of inclusivity? Foundation models are trained on the vast, unfiltered internet, which means they inevitably reproduce stereotypes about race, gender, culture.
That's a challenge of scale. The models reflect the data they ingest. One critical finding noted in the research is that because so much of the internet data used for training is English and heavily Western-centric, the models implicitly learn the cultural norms of what researchers call weird societies.
WEIRD, what does that stand for?
It stands for Western, educated, industrialized, rich, and democratic. These populations just have a disproportionately large digital footprint. So when the agent is tasked with a decision or an inference related to social norms, it often defaults to these weird cultural assumptions, and that leads to overgeneralization and marginalizing other viewpoints.
The model is learning the cultural blind spots of the people who created the data. So how do researchers enhance an agent's natural reasoning, its ability to make sound inferences, while trying to bypass these biases?
That whole process is called inference augmentation. It's about boosting the agent's predictive capabilities. We see techniques like data enrichment, where you incorporate external, highly contextualized data, or algorithm enhancement, which might mean combining NLP modules with more robust image recognition tools.
But when you're dealing with ambiguity, with ethics, with cultural sensitivity, places where even humans struggle, a technical solution just isn't enough.
It's not. And that's why the most crucial element in inference augmentation is the human-in-the-loop approach, HITL. In high-stakes environments, human judgment is deliberately integrated to guide the agent's inferences, to provide those ethical checks, and to handle situations where the data itself is ambiguous or biased.
Let's shift focus now and see these sophisticated agents in action, starting with the environment that has really become the perfect training sandbox for AI video games.
Gaming is being fundamentally transformed. Historically, non-player character, or NPC, behavior was so tedious. It was just a series of if-then scripts. If the player approaches, then the NPC says line A, Agent AI uses LLMs to give NPCs contextual memory, the ability to form relationships, to follow daily schedules. This moves them to true autonomy and adaptability.
So they're not just standing there waiting for the player to initiate a quest. They actually have a virtual, evolving life.
Exactly. Researchers demonstrated the emergence of these generative agents in 2023, where characters remember complex events and react to novel situations in ways that surprise even the programmers. And to quantify this complex social behavior, researchers created a new test bed called Cuisine World.
Cuisine World, is that like an AI version of that famous collaboration game?
It's a text-based game focused on multi-agent collaboration, and it's very similar to the fast-paced kitchen chaos of the game Overcooked. It demands real coordination. And to measure success, it introduced a metric called the collaboration score, or COS, which is designed explicitly to quantify how efficiently agents and human players collaborate under pressure, rather than just measuring if they completed the task. It's measuring the quality of the interaction.
That's a great transition from virtual autonomy to physical action. Robotics. In this field, the agent has to move beyond just conversation and actually manipulate the real world safely.
This is where that multimodal integration becomes absolutely essential. Two concepts are key here. First, visual motor control. This is the ability to interpret visual data in real time to adjust motor actions. It's crucial for detecting execution errors. If the robot sees the object slipping, it has to adjust its grip immediately.
And the second concept, that bridges the human command gap.
That's language-conditioned manipulation. This uses the LLM's understanding of natural language to interpret complex instructions, and it dramatically lowers the barrier for human-robot interaction. Instead of coding specific movements, you can just tell the robot in plain English, clean up everything on the table, and place the red cup on the shelf.
The sources gave a great example of this, the ChatGPT-empowered task planner. How does that show the power of language for real-world execution?
It's fantastic because it combines complexity with safety. The system takes a user's natural language instruction and a detailed description of the environment, and the LLM acts as the planner. It generates a fully decomposed sequence of subtasks for the robot. And crucially, that final generated plan is shown to the human for review and adjustment. You can critique the plan before the robot ever moves a joint, which ensures safe operation and human accountability.
And that need for human accountability leads us right to the highest stakes application, healthcare. The dual potential and risk here are just immense.
It is a profound area. Diagnostic agents, chatbots, and multimodal systems used for triage or initial diagnosis, they promise to improve equitable access to care globally, especially in areas with limited medical resources. But the risk of hallucination here isn't just an error, it's a catastrophic failure.
If an agent gives a misdiagnosis based on an extrinsic hallucination, what are we talking about in terms of real-world consequences?
We're talking about postponed treatment, or worse, incorrect treatment, leading directly to severe injury or death. This is the very definition of a catastrophic outcome.
Given that level of risk, how are developers handling the danger of an autonomous agent making a life-or-death decision?
The models are being intentionally and severely constrained. If you look at current multimodal agents like GPT-4V, while they have significant medical knowledge due to mandated safety training and strict ethical boundaries, they often explicitly refuse to provide prescriptive or diagnostic queries.
Can you give us an example of that kind of refusal?
Yes. The sources note that the model might decline to analyze a high-resolution image of a skin lesion for diagnosis, or it might refuse to interpret an EKG scan and suggest a course of action. This shows a clear, active constraint being enforced in these critical domains. It prioritizes safety over full autonomy.
Sure.
It's the agent basically saying, I know the answer, but I'm not allowed to tell you what to do.
That is the central tension of the entire field, isn't it? The agent is too knowledgeable to ignore, but too dangerous to fully trust. Before we conclude, let's quickly touch on how these agents acquire their skills. We have the well-known approach of reinforcement learning, RL, where the agent learns from massive amounts of data through rewards and penalties.
And contrasted with RL, you have imitation learning, or IL. This is often based on behavioral cloning, where the agent skips all that complex reward calculation and learns simply by mimicking expert data, just copying the actions of a human demonstrator, for example.
But for an embodied Agent 1 designed to operate a robot in reality, most of that learning happens in a simulation, which is a perfect world. If you deploy an agent trained in a perfect world into our messy, unpredictable reality, performance must degrade.
That is the single biggest technical challenge for embodied agents, sim-to-real transfer. Simulations inherently fail to replicate subtle, real-world factors, tiny variations in friction, shifting lighting conditions, sensor noise, unexpected disturbances. The learned policy just degrades so quickly when you deploy it physically.
So how are researchers actively trying to bridge that uncanny gap between simulation and reality?
They employ several robust techniques. One is domain randomization. This means they purposefully vary key simulation parameters during training, like the textures of objects, the lighting, the sensor noise. This forces the agent to learn a robust policy that is indifferent to real-world variations, making it less brittle when it's deployed.
It's almost like you're training the agent in a confusing, chaotic version of reality so that actual reality doesn't shock it.
Exactly. And the other key technique is domain adaptation, which often uses generative models like CycleGAN to bridge the visual gap. These techniques translate images between the simulated domain and the real domain, making the agent's visual input look more realistic, even if it was trained in a simple environment. And it does this without needing perfectly matched, paired examples of simulated and real images.
This entire deep dive shows we are truly moving toward these holistic, multimodal agent AI systems that seamlessly integrate language, vision, and physical action. The power of LLM and VLM integration is unlocking a level of automation and creative enablement we couldn't have imagined just a few years ago, from making virtual characters feel like real people to providing initial medical triage.
It's transformative, but the development of agent AI presents us with this profound and continuous trade-off. In critical, high-risk domains like healthcare, agents are being deliberately constrained by safety training, limiting their diagnostic autonomy to prevent catastrophic errors.
Yet, in open-ended fields like gaming or creative design, the entire goal is the opposite. It's all about maximizing unpredictable behavior, open-ended generation, and artistic freedom.
It's a fundamental philosophical impasse, and it's driven by application. The provocative thought for you to consider is this: how far can we truly push an agent's reasoning and adaptability, it's Aristotelian final cause, before we have to mandate that it stops thinking freely in the name of universal safety? And will the demand for customization in one domain always clash with the fundamental need for strict ethical constraints in another?